Hi, my name is Ashley Trainer, and today I will be presenting my project on mortality prediction in the ICU. Big data technologies and advanced analytics are becoming prominent in many industries. They make it possible to build faster and more complex tools that are scalable, increasing decision-making capabilities of their users. Healthcare specifically has potential to use these technologies to determine a more optimal approach to patient care. Particularly in the ICU, understanding the patient's disease state is monumentally important. However, it is also one of the most challenging settings to understand patient state because of their quickly evolving nature. Ghassemi and others examine the use of latent variable models to decompose free text hospital notes into meaningful features, and the predictive power of these features for patient mortality. The goal of the study is to recreate their work using big data technology. Our final cluster configuration for this experiment used the AWS R3 instances that are optimized for memory-intensive applications and have the lowest cost per gigabyte of RAM among Amazon EC2 instance types. We used 3 R3 extra large instances for our worker nodes and an R3 large instance for our master. We had 12 cores and approximately 90 gigabytes of memory as well as 80 gigabytes of storage. All of our data was stored in CSV format in an AWS S3 bucket. We developed our Spark application locally using Scala and then moved it to the cluster to run. Apache Spark is an open-source distributed processing engine that uses the speed of in-memory computing in order to process big data very quickly. MLlib is Spark's machine learning library that implements many of the widely used machine learning algorithms and other utilities in a distributed fashion. We built this analytics architecture in order to take advantage of our distributed computing to be able to process this large quantity of data in an efficient manner. We pulled our data from Mimic 2 2.6 version 26 database, which encompasses virtually all patients admitted to ICUs at Boston's Beth Israel Deaconess Medical Center during the period of 2001 to 2007. We pulled 35 features for each patient, including gender, age, SAPS-1 score on admission, minimum and maximum SAPS-1 scores, and the 30 more comorbidities as calculated by ICD-9 codes. Gender and the comorbidities are binary features. Age and SAPS-1 score features were scaled for model performance. In addition to these 35 features, we also derived 20 additional topic distribution features based on free text notes. Data was filtered to exclude patients with missing data points as well as all patients under 18 years of age. We used latent Dirichlet allocation for our topic modeling. LDA is a 3-level hierarchical Bayesian model that produces a set of topics that represent unobserved groups that can explain the data we're analyzing. We use the implementation provided in Spark MLlib for our research. The input to the topic model was filtered and tokenized vocabulary for each patient. We also experimented with stemming each individual word within a patient's notes to increase performance. We used EMLDA optimizer, which uses expectation maximization on the likelihood function to learn clustering as our optimizer. We ran the algorithm with a maximum of 75 iterations. The output of the model was 20 topics, and from that we were able to obtain the distribution over these topics for each patient. These distributions were used on our topic models as individual features and allowed us to add information from free text as structured topics. We focused on predicting 3 separate outcomes for this experiment: in-hospital mortality, 30-day post-discharge mortality, and 1-year post-discharge mortality. We considered 3 different sets of features as well as combinations of the 3 for model input. These were baseline features, derived features, and topic features. Baseline features were age, gender, and SAPS-1 score on admission. These were pulled directly from Mimic 2 and were collected on admission to the ICU. Derived features include minimum and maximum SAPS-1 scores, as well as 30 comorbidities calculated from ICD-9 codes. These are retrospectively calculated based on data collected during a patient's stay at the ICU. We also had 20 topic features that represent the distribution of each topic per patient. These features are based on topics generated from patients' notes that were collected throughout their stay at the ICU. Using these features, we trained the following model: a baseline model, which used only admissions features; derived model, which uses baseline features and derived features; topic model, which uses just the 20 topic features; baseline and topics model, which uses baseline and topic features; an all feature model, which uses all baseline, derived, and topic features. Because there was such a large class imbalance for all 3 outcomes, we used subsampling on the negative class to create a 70-30 split of the negative and positive class data. This was only applied during training, so our test set does represent the actual separation of positive and negative class. We trained a separate SVM and decision tree for each of our model and outcome combinations, and each model was tuned using cross-validation. The most successful model was then trained on the entire training set and tested using a separate test set data. We primarily used AUC to evaluate the predictive power of our models, though we also considered sensitivity and specificity because of the imbalance in class. We used our baseline model to compare against the other models in order to determine the value of our topic and derived features. Overall, our decision tree did not perform as well as our SVM, and specificity was strictly larger value than sensitivity for almost all models, most likely due to the class imbalance. In-hospital prediction performed significantly better than 30-day and 1 year, and this seemed reasonable to us because those with the strongest indicators for mortality are more likely to pass away while in the ICU, and those who pass away after being discharged could be influenced by other factors that we cannot include in the model. Our highest performing model was our baseline and topic model for predicting in-hospital mortality using topics derived from the STEMmed vocabulary. Just like to take a second to thank all of my classmates who have been working so hard this year and have supported me on discussion boards and through peer review of this project. Thank you also to Professor Sun and all of the TAs for all of their support throughout this project and the entire semester. Thank you.